Hello everyone, my name is Akanksha and today I would like to give demo on the topic of reaction intermediates. So particularly here we will be discussing about carbocations, carbanions and free radicals. So before heading towards the reactive intermediates, let us define what do we mean by the term reactive intermediates. So reactive intermediates are the species which are formed during a course of a reaction and they are destroyed at the end of the process. Alright. So reactive intermediates are the species which are formed during the course of a reaction and destroyed at the end of the process. So I can say reactive intermediates are short-lived, highly reactive, unstable species. Okay, reactive intermediates are short-lived, highly reactive, unstable species. Alright. So suppose I have a certain reaction, that is A plus B, it is forming a product as C. Right. So during this formation, the reaction proceeds through a step which is called as intermediate step. So A plus B giving AB star, which further forms C. So this reaction is proceeding via this step, that is formation of AB star. So I can say the formation of AB star, but more probably AB star is my intermediate. Okay, intermediate. So this is all about the information about reactive intermediates. Alright. So now this reactive intermediates, they are classified into 6 main categories. So the first one is carbocation. Second one is Carbanion. Third one is the free radical. Fourth one is my carbene. Fifth one is my nitrene. And the sixth and last one is benzyne intermediate. So we can say during any organic chemical reaction, these 6 intermediates are formed in a particular reaction. Right? So here we will be more and more focused on these 3 intermediates, that is carbocation, carbanion and free radical. First reactive intermediate, that is carbocation. So what do we mean by the carbocation? So carbocation is the positively charged species which is formed by heterolytic fission. Okay, heterolytic fission. So what do we mean by the term here, heterolytic fission? So fission means the breaking of bond. So now breaking of bond can take place in 2 different ways. One is heterolytic fission and the other one is homolytic fission. So as I have mentioned, the carbocations, they are formed by heterolytic fission. So heterolytic fission is the unequal breaking of bond. Okay. So I can say carbocations are formed by unequal breaking. So due to heterolytic fission, there is a formation of ions. So ions can be positive or negative. So here, as I said, carbocations are positively charged species. So this leads to the unequal. This is formed due to the unequal distribution of electrons. That is heterolytic fission. Next one is the outermost electrons which are there in the carbocations. So for that, let's see the structure of carbocation. So the structure of carbocation can be drawn like this. Carbon, it is forming 3 sigma bonds and containing vacant p orbital here and 1 positive charge. So this is my structure of carbocation. So most of the information can be, or the characteristic features of carbocation can be described by this structure. Okay. So as I can see, it is here there is a presence of vacant p orbital. Okay, vacant p orbital. All right. So I can say carbocation, it consists of vacant p orbital. Alright. Carbocation consists of vacant p orbital. Furthermore, I can see it is forming 3 sigma bonds. First one, second one and the third one. So I can say carbocation, it forms 3 sigma bonds. Okay, 3 sigma, that is, this is the notation for sigma bond. So I can say carbocation forms 3 sigma bonds. Okay. So when there is a formation of 3 sigma bonds, no, so the outermost electrons will be 6. Okay. So I can say carbocation consists of 6 outermost electrons. Okay. 6 outermost electrons. So this was about the characteristic features. Now I have to see the hybridization of this carbocation. Okay. So I can see here it is forming a trigonal like structure. Okay. Like this. Okay. So I can say the hybridization first. Okay. The hybridization of carbocation, it is sp2. Why sp2 here? Since it is forming 3 sigma bonds. Okay. So sp2. Right. So means 1s orbital and 2 p orbitals are involved in formation of carbocation ions. Okay. So this is the hybridization. Now shape. When the hybridization is sp2, the shape will be trigonal planar. Okay. Trigonal planar. Alright. So this was about the carbocation. Furthermore, I can say since carbocation carries positive charge. Okay. So I can say it is the electron deficient species. Okay. Carbocation is electron deficient species. What do we mean by the term electron deficient? In order to attain the stability, it will require electrophile, or it acts as a electrophile. Okay, it has to attain the stability, no? So it requires certain electron-rich species which can be attached to them, and it will be electron-rich. So I can say carbocations here, they act as electrophiles. Okay, electrophile, or it consists of positive charge. Okay, E plus. Okay, so now let's discuss about the stability here. Okay, so as it is electron deficient over here, so I will require electron donating groups, right, to increase its stability. So stability will be directly proportional to the electron donating groups. Okay, stability will be directly proportional to the electron donating groups, whereas it will be inversely proportional to the electron withdrawing groups. Okay, electron donating groups will increase the stability of carbocations, whereas electron withdrawing groups, they will decrease the stability. Okay. Now what are my electron donating groups? The examples can be alcoholic group, alkyl groups, etc. These are my electron donating groups. They will increase the stability. Whereas electron withdrawing groups can be halide groups, that is X, and furthermore ketonic or aldehyde group. Okay, this is aldehyde group. They are electron withdrawing groups and they will decrease the stability. Furthermore, the order of stability is in terms of carbon atoms. Tertiary carbocation, that is 3 degree, it is more stable as compared to secondary, which is further more stable to the primary. Okay. Now what do I mean here by tertiary? Tertiary means the carbon atom will be attached to 3 different carbon atoms over here. Okay. When single carbon atom is attached to the 3 different carbon atoms, I would call it tertiary. Okay. So this carbocation will be more stable as compared to secondary. Now secondary, what do I mean? I mean by the term secondary, it will be attached to 2 different carbon atoms. Okay. So one carbon atom, your hydrogen is there, it would be attached to 2 different carbon atoms. So this is my secondary. Now primary will be no any like carbocation will be attached to only one carbon atom, I can say. So this is the case for primary, secondary and tertiary. So this is the order of stability. Now furthermore, let's discuss how can we generate the carbocations. Okay. So next topic will be generation. Okay. So there are various ways in which carbocations can be generated. The first one is protonation of alkene, and the second one can be protonation of alcohols. Okay, protonation of alcohols. Now here, what do we mean by the term protonation? Protonation means addition of hydrogen. Okay, when hydrogen are added to the alkene or alcohols, we get carbocation as an intermediate. Okay, now let's see the reactions which involve carbocation. Okay, reactions involving carbocations. Okay, carbocations. So the reactions which involve carbocation as the reactive intermediates, they are, the first one is rearrangement reaction. Rearrangement reactions which mainly involve carbocation intermediate, and the second one is pinacol-pinacolone rearrangement. Okay, pinacol-pinacolone rearrangement. So this was all about the carbocation intermediate. We have discussed its characteristic features, structure, generation and reactions which involve carbocation. Now let's begin with another reactive intermediate, that is carbanion. So now what is carbanion? Carbanion is the negatively charged species, formed by heterolytic fission again. Okay, formed by heterolytic fission, right? Heterolytic fission. So in the case of carbocation, we have discussed about heterolytic fission, that is unequal distribution of electron, and there is a formation of ions, that is positive or negative. Alright. So now let's see the structure of carbanion. Okay. So the carbanion, no, it carries one negative charge over here, like this carbon atom, forming three different bonds, I can say, and one lone pair is also there. Here there will be formation of one lone pair and negative charge. So this is the structure of my carbanion. Okay, structure of carbanion. Right. So my carbanion, it carries one negative charge and one lone pair. So here I can write again, carries one negative charge and one lone pair. Okay, one lone pair. So I can say in the outermost shell there are, as it is forming 3 sigma bonds, like 1, 2, 3. So 6 electrons and 2 lone pairs, that is total it carries 8 outermost electrons. So carbanion has 8 outermost electrons. 8 outermost electrons. So this is the case for carbanion. It carries 8 outermost electrons. Furthermore, let's see the hybridization and structure. I can say hybridization and geometry of the carbanion. Okay. So here you can see it is forming 3 sigma bonds and 1 lone pair. So there are the 2 possible cases for structure and hybridization. Okay. Hybridization can be sp2 or sp3 as well. Okay, sp2 or sp3. Now there is a certain condition. Okay, when this lone pair, no, it will participate in the resonance. So at that time sp2 hybridization will be observed. Okay, here lone pair participates in resonance. Okay, so when there is a participation of lone pair in resonance, the hybridization will be sp2. Rest in other cases, the hybridization will be sp3. Now, when there is sp2 hybridization, the shape will be again trigonal planar, and geometry will be for sp3. sp3, the geometry will be tetrahedral, I can say. Okay, tetrahedral, or more probably I can say trigonal pyramidal. Okay, trigonal pyramidal. So this is the case when the hybridization is sp3. Furthermore, as Carbanion, it is electron-rich species. Why it is electron-rich? As it carries one negative charge over here. So I can say Carbanion is electron-rich species. Okay, it is electron-rich species. So it will have affection towards nucleophile. I can say it acts as a nucleophile probably. Okay, so it acts as a nucleophile. Okay, nucleophile. So this was the case, or these are the characteristic features of Carbanion. Furthermore, let's discuss about the stability over here. As it is electron rich, so it will be directly proportional to the electron withdrawing groups. Okay, so stability, it is directly proportional to the electron withdrawing group, and it would be inversely proportional to the electron donating groups. What are the examples of electron withdrawing and electron donating groups? Which this we have discussed in the case of carbocations. Okay. Furthermore, again, when there is tertiary, secondary, or primary carbanion, so what would be the stability? Okay, the stability will be here. The case is opposite as that of carbocation. Here 1 degree carbanion will be more stable than 2 degree and then 3 degree. So 1 degree, as we have discussed, when one carbon atom carries negative charge, it is called as primary. When the carbanion is attached to 2 different carbon atoms, I can say it is secondary, and when it is attached to 3 different carbon atoms, it would be tertiary. Okay. So this is the order of stability of carbanion. Now let's discuss about the generation of carbanion. How carbanions are generated. Okay. So the reactions of generation of carbanion, it involves 2 steps. Okay, the first one is from unsaturated compounds. From unsaturated compounds. Unsaturated compounds means it can be alkene or alkyne. Next one is the by proton abstraction by a base. Okay, proton abstraction by base. Okay, when there is abstraction of proton from a certain base, base can be, examples of bases are aqueous NaOH, tertiary butyl hydroxide, etc. Okay, when these bases are present, there is abstraction of proton by these bases and we get generation of carbanion. Okay, next one, let's discuss about the reactions involving carbanion. Okay, reactions involving carbanion. Now there are certain reactions which involve carbanion as the reactive intermediate. So the first reaction can be elimination reactions. Okay, elimination reactions, and the second one is addition reactions. So there are various addition reactions in which we get generation of carbanions. Okay, generation of carbanions. So this was all about carbanion intermediate. We have discussed generation and reaction and characteristics. Towards the next reactive intermediate, and that is free radical. So let's define what do we mean by the free radical. So free radical is the species which contain one unpaired electron in its outermost shell. Okay, one unpaired electron in its outermost shell. Okay, so we can say there is a presence of one extra electron over here. Okay, in its outermost shell. So in order to describe further characteristic features, let's draw the structure of free radical. Okay, so the structure of free radical can be drawn like this. Here carbon is forming 3 sigma bonds, alright, and there we have one p orbital, and this p orbital consists of one unpaired electron here. So this is the structure of free radical. Okay, free radical. So my free radical, it consists of one unpaired electron in the outermost shell of p orbital. Okay, so I can say free radical, no, it is a 7 electron species. Okay, that is outermost shell consists of 7 electrons. Right. So furthermore, again moving towards the next point, we will be discussing about hybridization here. Okay, so as I can see, this carbon atom, it is forming 3 sigma bonds, right? 3 sigma bonds, whereas this is one odd electron, we can see. You can neglect this odd electron over here. So here the hybridization would be sp2. Okay, why sp2? Since it is forming 3 sigma bonds. Okay, and we have calculated total electron, that is 7, that is 3 sigma bond. Okay, and one unpaired electron. Okay, one unpaired electron. So this is about the hybridization. Now let's see about the structure. Okay, now it is looking like a trigonal planar geometry, which we have discussed in case of carbocation, right? So if I join these points, so I can say free radical, it has a structure of trigonal planar. Okay, trigonal planar. So now normal carbon atom, it consists of 6 electrons, right? Here I can say free radical is also electron deficient species. Okay, it is also electron deficient species. Okay, which means it acts as a electrophile. Electron deficient species means it acts as electrophile. Okay, it has certain similarities, I can say, with carbocation. As you can observe, here hybridization is also same as carbocation. Similar way, structure is also same, and is electron deficient species. Alright, so I can say free radical is somewhat similar to carbocation. Furthermore, let's discuss about the stability over here. Again, the stability would be same as that of carbocation. Stability will be directly proportional to the electron donating group, and it would be inversely proportional to the electron withdrawing group. Okay, the examples have been discussed earlier. Similarly, this tertiary carbanion, okay, tertiary carbanion would be more stable than secondary than primary. Okay, now carbanion, it carries one radical like species. Okay, so I can draw the structure like this. This is my carbanion. So when one carbanion is attached to 3 different carbon atoms, I can say it is tertiary. So this one is my tertiary carbanion. Alright, then again, when it is attached to 2 different carbon atoms. Okay, so this is my secondary. When it is attached to 3 hydrogens only, no carbon atom, or I can say single carbon atom, so I can say it is primary. Okay, so this is my primary carbanion. So this is the order of stability in terms of attached carbon atoms. Alright, now let's discuss about the generation, how free radicals can be generated. Okay, so generation of free radicals, no, it can be observed in 2 different reactions. Okay, first one is the photolysis reactions. Okay, photolysis, and second one is the thermolysis. Okay, thermolysis. Now, as the name suggests, photolysis means it involves light or photons. Okay, that is H nu. And thermolysis means it requires heat. So here generation of free radical involves photolysis as well as thermolysis. Photolysis means involvement of light, and thermolysis means involvement of heat during a chemical reaction. So the free radicals can be generated by these 2 ways. Next one is the reactions. Okay, so reactions which involve free radicals, okay, involving free radicals. So let's discuss what are the types of reactions which involves free radicals, okay. So the first one is the recombination reaction, okay, recombination reaction, and second one is the disproportionation reaction, okay, disproportionation reaction. So these two reactions involve free radical as the reactive intermediate. So this was all about the today's demos class, in which we have discussed about carbocations, carbanions and free radical, their characteristic features, structure, generations and reactions. Thank you.